Hello, everyone. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. I hope you're ready. I hope you're excited. This guy's excited. Are you excited? Let's do this. We're going to talk about periodic trends today. Trends in the periodic table. We've defined some of these terms already in the previous video. We're going to talk more about them, kind of summarize them, talk about why they work. That's our goal here today. Now, how often do I like jokes about chemistry? Periodically. No comment. All right. Coulomb's law, Coulombic, I think that's how you say that. Coulomb's law is the main thing that we're going to be talking about here that has to do with these periodic trends. And, you know, we don't need to know a ton about it, but basically it says some sort of common sense things, or things we know about from other science classes. It says opposites attract and like charges repel. And the more charge, the more repulsion, or the more attraction. So +1, -1, they attract. +2, -2, they attract more. And the same thing with the repulsion when we're talking about positive charge. And then the other thing here is the distance. The distance makes a huge difference. As the distance between two charged particles increases, the amount of attraction or repulsion goes down very quickly. It's technically inversely proportional to the square of the distance. So if you understand kind of about math, that means the distance makes a big difference. I'd ask you here to think about two magnets, like if you've ever played around with really strong magnets. When the magnets are close, you know, they can be, especially strong magnets, they can be almost difficult to pull apart. But as you pull magnets away from each other, that attraction goes down very, very quickly until you don't have to hold magnets very far apart at all before there's almost no attraction between them seemingly. So distance makes a big difference. So a concept we're going to talk about here is called shielding. And so protons are positive, they're in the nucleus, electrons are negative, and of course there's an attraction between the electrons and the protons. So what's true, though, is that some of the attraction is, to a degree, canceled out. Now, here's what I mean by that. When we're talking about this attraction, we're talking about the attraction between these valence electrons, the outermost electrons, because they're kind of the most important ones in chemistry. What's the attraction between these electrons and the nucleus? The thing is, protons are positive, electrons are negative, so this electron is attracted to the nucleus, but it is being repelled by these electrons that are the interior electrons. So between this electron, which is negative, and this positiveness here in the nucleus, there's some negative charge that's going to cancel that out. Same thing with the chlorine. And we're going to view these valence electrons kind of collectively. They have the same, what we call effective nuclear charge. So effective nuclear charge, ZF, remember we talked about Z, that's the number of protons. So the nuclear charge in the case of sodium is +11, but that doesn't mean that this electron out here is feeling +11 worth of charge. That's called the effective nuclear charge, and I'm going to talk about that here on the next slide. So, by the way, when it comes to sketching these Bohr models, hopefully we've talked about them in class. You certainly don't need to sketch these Bohr models like over and over again. If you want to sketch them once is plenty. But anyway, sodium is said to have an effective nuclear charge of +1. This is because, again, when we're viewing this, we're just thinking about this valence electron. In between this electron and the nucleus is 10 electrons. So we have 11 protons, that's +11. 10 electrons cancel out like 10 units of charge from there, so the remainder is +1. +11 -10, it's +1. That's what this electron is feeling. Chlorine, on the other hand, so it has 17 protons, so its nuclear charge is +17. And then again, when we're thinking about what these electrons experience, we're just kind of thinking about them as a whole. In between these electrons and the nucleus, again, is 10 electrons worth of shielding. So +17, these 10 electrons cancel out like 10 of that, so that leaves +10 remaining. 17 protons blocked by 10 interior electrons. The outer electrons, all of these are feeling a +7 effective nuclear charge. So, you know, I get this shielding, it can be a little confusing at first, but just for funsies, let's try this right here. I want you to take a look at calcium. Here's calcium's Bohr model. There's an isotope with 20 protons and 20 neutrons. What's the effective nuclear charge for these electrons out right here? So hopefully you got +2. 20 protons, that's positive 20. If you count these interior electrons, there's 2, and then there's 8, that's 10, and another 8, that's 18. So there is 18 electrons in between these two valence electrons and the nucleus. So positive 20 canceled out by 18 negative units of charge. These guys are experiencing a effective nuclear charge of +2. You know, you don't need to sketch this or anything necessarily, but just what's going to happen is effective nuclear charge is going to increase as you go across the periodic table. And, you know, we're going to talk more kind of about how that's working and all that stuff. Another thing to think about, and this is going to be reiterated later, and we're going to talk more about it later. What's also true is you go down the periodic table, actually the effective nuclear charge is +1 all the way down column 1. However, the other factor that comes into play is distance. The distance is going to be increasing as we go down, which is going to actually decrease that attraction for the outermost electrons. So, hopefully, you know, some people have this reaction when they're talking about this shielding and the effective nuclear charge stuff and all that. You know, if that's you, maybe go back, rewatch this a little bit, ask questions in class, we'll talk about it. And again, we're going to kind of continue to develop these ideas, but hopefully you're feeling decently solid, and then we're going to try to relate this to the periodic trends that we've already talked about. Oh, but first, you know, some of these jokes, this one's older than dirt, you know. What do you do to dead chemists? Bury them. Yeah, I've been hearing that for years. And then, you know, sometimes they try to slip these past you. That's my element, nap. I mean, come on now. Adamantium, that's not even real. But, you know, sometimes they'll try to slip one past you here if you look up periodic table jokes. All right, anyway. This is just a drawing of atomic radius, or I should say a sort of a schematic of atomic radius, and it's basically got the middle section of the periodic table cut out. So we can see there's definitely a trend here. We can see that the atoms are getting smaller as we go this way and larger as we go down. So that's one of the trends in the periodic table, is that there's that particular pattern that we observe with atomic radius, which we defined in the last video. So basically, when it comes to periodic trends, there's a couple things we need to be able to do. We need to be able to say, what are the patterns in this particular thing, like with atomic radius, we just looked at that pattern, and then we need to be able to explain them, and that's the much harder part. But what I would suggest that you do is that you draw just any kind of really rough outline of a periodic table, or even just a rectangle is fine. And we're going to label this rectangle with the direction where the trends increase. So as we saw in the last slide, atomic radius gets bigger as you go in this direction, from right to left. So that's where we point our arrow going that way, and they also get bigger when you go down. So it makes francium the biggest atom, and it can help to if you can just know what the biggest atom is, that can help you remember what direction the trend goes. So francium's the biggest, and then therefore it's going to increase going towards francium. Ionization energy goes up as we go up, and up as we go to the right. So again, that's the energy to remove an electron from an atom in the gas state, as again we defined in the last video. So that makes helium. Helium has the very highest ionization energy. And then electronegativity. Electronegativity is a tendency to attract electrons in a covalent bond. Fluorine has the very highest electronegativity of all the elements. This is very important to pay attention to. The noble gases are not included in the electronegativity trend. You know, if you just looked at these arrows, you would think the most electronegative is helium, but it is fluorine. The noble gases are, however, included in the other two trends. So specifically with the electronegativity, the noble gases are not included in that trend. So basically we have to be able to do two things. We have to be able to look at a list of 2 or 3 elements and say which one is going to be the larger one or going to have the greater ionization energy, so sort of rank these things by these trends. Or so that's one thing, but then we have to be able to try to explain them. So I'm going to put some practice here into the Edpuzzle video, and we'll just do a little bit of that ranking, and then we'll talk about how to explain these trends. Okay, so explaining these trends is something we're going to work on quite a bit. It's difficult, and for a lot of people it is difficult, and it's going to come down to this. All these trends basically work for these reasons, and when we're explaining a periodic trend or saying like why it happens the way it happens, these are the things that we're going to talk about. The key to what happens when we move left to right is this. As you move across the same energy level, the number of protons is going up, but electrons are going into the same energy level. So as we go across this period 2 here, there's more electrons each time. There's more electrons and protons as we go across, but these electrons are being added to the same energy level. That's going to increase the attraction for electrons. As we move down, what's very critical and important there is that every time we go down a row on the periodic table, there's one more energy level for electrons. First period has 1 energy level, second period has 2 energy levels, third has 3, and so forth. So that's going to be the distance part of Coulomb's law, and so the attraction for electrons is going to go down. And all of those trends that I just mentioned, these are the reasons that they work. And basically, if we're asked to explain periodic trends, we're just going to apply it to the particular situation that we're going to be asked about. So for example, the atomic radius trend. Let's go back to that slide. If we're asked to explain why is it that atoms get smaller as we go this way, it has to do with the fact that there are more electrons and protons as we go this direction, but, and this is very key, the number of energy levels remains the same. So therefore, since there's more energy levels, there's more, since there's the same number of energy levels but more protons, the attraction for those electrons is going to get smaller. So as we go across, those outer valence electrons are going to get pulled in tighter and tighter and tighter by those number of protons, and it's going to make the atom smaller. Remember, the nucleus is very, very small compared to the electrons. So it's really the electrons that determine the size of the atom. The nucleus's size is insignificant. So we go across the periodic table, we add protons, number of energy levels remains the same, those electrons get pulled in tighter and they get smaller. Now, as we look going down, the number of energy levels is going up, and that's basically the main thing that's making the atom larger, is that as we go, we're sort of stacking another energy level every time we go down, so that's a greater number of energy levels, the atom is going to get larger. A common mistake that people will say, and something you want to avoid, is they'll say atoms get smaller as you go to the right because there are more protons and there's more attraction, period. They'll just say more protons. The reason that doesn't work, the reason it's very important that you add the fact that the number of energy levels is remaining the same as we go to the right, is the number of protons and electrons is going up in both directions. It's going up as we go down, and it's going up as we go to the right, yet the atoms get bigger going down and they get smaller going to the right. So it's very key when we're talking about these trends that we talk about the effect that additional energy levels have. Now I understand this can be a little mind-blowing for folks, but we will definitely be talking about this more. So, if you have a little trouble understanding what I'm saying, we'll talk about it and continue to develop these ideas in class. So something else that needs mentioning is ionic radius. So don't mix that up with atomic radius. Atomic radius is uncharged atoms. Now we're talking about the radius of ions and what effect that has. So basically, metals are going to form positive ions. They're going to lose electrons. They're going to get smaller when they do that. The main reason for that is because they're generally going to lose a whole energy level to get that full stable energy level that we've talked about, I think, and I hope that we've talked about. So the atoms lose an entire energy level. They're going to get smaller when they do that. But also, when we're talking about within a period, within the same row, the metals are going to get smaller as we go to the right because the positive charge is going to get greater. And I'll show you a diagram and explain a little more about what I'm talking about with that. So nonmetals, what happens with them is they gain electrons, and they're going to generally get larger because they're going to be they're not losing entire valence shells, they are gaining and filling up their valence shells. So the more negative the charge, that generally makes the nonmetal ions larger because there's greater repulsion between the electron shells. So again, that's kind of the gist of it. Let me show you a couple things to try to help you understand that. So this is a sodium atom with no charge, so 11 protons, 11 electrons. Now, when it forms an ion, which is a +1 ion, that's what it forms, it's going to lose that entire outer energy level. And so, yeah, it's going to get smaller because now it only has 2 energy levels for its electrons. And not only that, though, now it's +1, so there's kind of an extra proton, if you will, that can pull those electrons in more tightly towards the nucleus. So for both those reasons, sodium atoms, when they form +1 ions, they get significantly smaller. On the other hand, chlorine atoms, so remember what this atom is going to tend to do is gain 1 electron here. It has 7 valence electrons. It's going to gain an 8th for stability. And it's going to get larger when it does that. So it's not losing a valence shell. It's gaining an electron in its outer valence shell. And that -1 is going to provide a bit of repulsion from the other shells. So it's going to cause the atom to tend to puff out and get a little bit larger. So looking at, this is just a 2-scale drawing, and we can see comparing the uncharged atom to the ion, we always get smaller. Now, what's true, though, is notice that here we have sodium, magnesium, and aluminum. They're in the same period of the periodic table. Notice that when we're talking about ionic radius, they get smaller as we go across. This is because they actually all have the same number of electrons, but their positive charge is increasing. When I say they have the same number of electrons, I mean the ions do. But the number of electrons, the positive charge is increasing. So Al+3 is really small because it's got like 3 extra protons that can pull those electrons in very tight and make it quite small. So that's what I was saying about within a given period, the ions of the metals are going to get smaller as we go to the right. Now that doesn't work all the way across, but at least for the metals in a given period, they're going to tend to get smaller as we go to the right with the ions. Here we have nonmetals forming ions, and they form negative ions and they get larger. So we can see that every time the negative ion is larger than the parent atom. And so again, this is because they're filling valence shells. They're getting larger. They're causing increased repulsion, which kind of makes the atom, the ion, kind of puff out a little bit and get bigger. Notice that within a period, it's kind of not super easy to tell from this drawing, but within a period, as you go to the right, the metal ions do get a little bit smaller. So now again, it doesn't get smaller all the way across, as we'll kind of talk about that, but at least comparing these three, you can see that N-3 is negative 1.71 is its radius, 1.36 is the radius of fluorine. So the ions too do get a little bit smaller. Are all the periodic table jokes gone? I don't think so, and neither does Chemistry Cat. So some other trends that we should talk about. Melting point. So basically it works like this. When you are talking about group 1, so the melting point for the metals in general, it doesn't work super well, but there is a pretty nice trend in at least the alkali metals in the first column. Melting point goes down as we go down. This is because the smaller the atomic radius, the closer the atoms are going to be able to bond to each other. Now I would say both of these, we're going to be able to understand these a lot better when we do our bonding unit and kind of talk more about what's going on with the bonding here. But basically, long story short for now, the smaller atoms of, let's say, lithium, which is at the top of the alkali metals, they can get closer together. They can form a tighter bond. It's harder to melt lithium. When you go down to like cesium, bigger atoms, they're a little farther apart. There's less attraction, and so cesium has a lower melting point. As far as the halogens, the trend moves in the opposite direction. Melting point increases as we go down, and this is because of increased London dispersion forces. Now, if you've had some chemistry before, maybe you know a little bit about that. But again, both these things we're probably going to have to really expand upon it and touch on it again when we talk about bonding. But I just wanted to mention it here because it is a trend that you need to know. So I thought it might be good to have in these notes. Another trend is reactivity. So we could ask ourselves, how vigorously will two elements react if we mix them together? what's important to remember is keep in mind where our sort of stair-step line in the periodic table is. This trend actually moves in opposite directions, depending if you're talking about the metal side of the periodic table or if you're talking about the non-metal side of the periodic table. With metals, basically, high reactivity goes along with low ionization energy because metals in chemical reactions tend to lose electrons. So if they have a low ionization energy, that means they easily lose electrons and they tend to be very reactive. So that means the bottom left is the most reactive metals. Francium, although francium is extremely rare, would in theory be like the most reactive metal because it has the lowest ionization energy. As far as nonmetals go, it goes along with electronegativity. The higher the electronegativity, the more reactive a nonmetal tends to be. So that means fluorine is the very most reactive nonmetal. Now remember, the noble gases don't count in the electronegativity trend. They're very, very unreactive. That's what's true about the noble gases. So fluorine is the most reactive nonmetal. So again, the trend in reactivity moves in opposite directions. So if we're evaluating reactivity, we have to think about what side of the stair step are we on and move in the appropriate direction based upon that. All right, guys, that is it. Thank you very much for listening. I know this stuff can be a little tricky. We'll definitely work more on it and practice it, and hope we'll get ourselves up to speed on periodic trends and explaining them. Thanks very much for watching. We'll catch you next time.